Hello everyone, my name is Mike Leffel. I am an application specialist at Roden Schwartz and I focus on nothing but vector network analyzers. In this presentation I'm going to talk about measurement uncertainty on S parameters. But not only that, I'm going to talk about the real-time calculation of measurement uncertainty on S parameters while they're being measured on a vector network analyzer. But not only that, I'm going to talk about the traceability of the calculated uncertainty back to a national metrology institute such as NIST in the United States or METIS in Switzerland. So the traceable measurement uncertainty calculated in real time on the vector network analyzer while we measure S parameters. So that's the focus of my talk today. And I'm only going to do this, I only have 15 minutes to cover this, so I have a very brief agenda. The first topic I'm going to talk about is which came first, the calibrated vector network analyzer or the characterized calibration kit. An interesting thought if you have never thought about that before, but which came first? From there we segue into the primary experiment. So how do we break that cycle? And who breaks that cycle? After a little discussion in that area, then we'll finally talk about what does this mean in practice to the real engineer. I myself I'm an engineer. I use the network analyzer to make S parameter measurements, as well as many of you. And so what I want to discuss is how do we, as engineers, take advantage of all the research that's occurring at the National Metrology Institutes, where measurement uncertainty is being improved from their research, and they're making progress in this area. How do we as engineers take advantage of that? How do we get our hands on the techniques and the technology that's being developed? So that's the focus of my talk. And I want to start with this question of which came first, the calibrated vector network analyzer or the characterized calibration kit. So of course you can see the circular logic. In order to characterize a calibration kit, I need a calibrated vector network analyzer. So how do we accomplish this? I'm not going to belabor the point. It's a little bit of a play on words, but this is a natural segue into what I call, or what's being called, the primary experiment. So who does the primary experiment and how do they create the very first characterized calibration kit, for example, for any particular connector series? So we all really need to answer the question, how do we determine what is the impedance of something at a particular frequency? And how do we trace that impedance back to a real world physical thing that we can measure? So that has to happen somewhere, and the question becomes, well, who's in the best position to do that type of traceability or that calculation of what is impedance and relate it back to a physical parameter? And how do they accomplish this? Well, the key thing is the coaxial air line. The coaxial air line is the one artifact that we can use that has physical dimensions that can be easily measured, such as the diameter of the inner conductor and the inside diameter of the outer conductor. And we have the equations and the knowledge about how electromagnetic waves propagate in the TEM mode down a coaxial transmission line. Since we have this relationship and this understanding of how electromagnetic waves propagate, we can then calculate from physical dimensions things such as the characteristic impedance of the line. And this is a key step that's needed in order to create, for example, the first calibration kit at a very high frequency such as 100 gigahertz. And I kind of alluded to this already. Who is in the best position to make this type of measurement, to do this calculation? And of course, it's our national metrology institutes. Each country has their own national metrology institute, which is tasked with this activity, basically making the most accurate measurements of things like time and distance, or the meter, and mass, or the kilogram, or the gram, if you will. And in the United States, it's NIST. They're tasked with this type of activity. In Switzerland, it's METIS. In Germany, it's PTB. And each country has their own National Metrology Institute. And these are the places that are in the best position to make these measurements, to do this primary calculation, using the tools and the techniques and the equipment that they have. And so that's what we're going to talk about a little bit next. So in this case, we're going to focus a little more on what's being done at METIS in Switzerland. So they are currently leading the way with respect to improving measurement uncertainty for S parameters. They have all of the equipment. I'm just showing some pictures in this slide, but they have all the equipment to do the physical measurements, such as, of course, measuring distance or diameter of a conductor, but also measuring surface roughness of a conductor, as well as measuring the coplanarity of, for instance, a waveguide flange or the connector that needs to mate, the male and female connector mating plane. And in addition, other things such as the concentricity of the center conductor and how round is something. So they have the tools, these National Metrology Institutes, they have the tools that are needed for this type of experiment, and they are in the best position. And what I want to talk about is what's been done at METIS at a very high level over the past decade in terms of how they've improved the measurement uncertainty of S parameters in a way, a very real way that we as engineers can take advantage of. Now, the very first thing I want to mention is the VNA Tools software. So all of these calculations of impedance traced back to physical dimensions, all of these calculations have to be done somewhere. And of course, in this day and age, we must use software to do these types of calculations. So they've created a package called VNA Tools, which does the calculation of what the impedance is, as well as all the other parameters that we need for a to create a characterized calibration kit. But it also calculates the uncertainty and the correlated uncertainties between different parameters that are being measured. And not only that, this software then propagates those uncertainties forward into the measurements that we make on the network analyzer, where we create the error model and the vector correction occurs. And finally, we make an S parameter measurement. So it propagates all of the uncertainties in the measurements of physical dimensions and everything else, and packages it and keeps track of it and carries it forward for us in a way that we can use. That is a key thing that's been that's required, and of course it's been developed in this case in VNA Tools at METIS. Now, other National Metrology Institutes have their own software packages for doing this type of calculation, but the one thing that's really important to point out is that this VNA Tools software is available free of charge to anybody. So METIS will share it with you. All you have to do is go to their website, register with your email, and it's just your email address. It's not anything fancy, and they will provide a copy of VNA Tools to you. What this means for us as practicing engineers is that all of the experts around the world have already downloaded VNA Tools and they've taken a look at it. And as experts, one of their goals, as we all have, is to find an error and become famous, so to speak. So if they can find something wrong with VNA Tools, of course they would point it out. So we know now that this software has been vetted by experts around the world. Everyone's looking at it. They can create their own test cases, and they can decide for themselves that, yes, this is working properly as expected. And of course, you have that ability as well. So to the extent that you want to create test cases and check things out, you can also do that in VNA Tools. It's free of charge. It's not open source software, but it's certainly open with respect to you can create test cases to see that it's working properly. Now, the next thing they developed at METIS was this what's called half connector model. So you have a mated connector pair, a male-female connected pair that's mated. They split that connector pair in half, I believe, at the calibration plane, and they spend a lot of time modeling the imperfections of these mated half connectors with the goal of being able to reduce uncertainty in that mated connector pair. So what can be done to make the connector pair more repeatable and more traceable, and then also to with the goal of de-embedding the imperfections of the connector pair. So I think a lot of work has been done in this area to improve the uncertainty contribution of the mated connector pair, to understand what's contributing and then remove that from the overall measurement uncertainty chain. And the last thing they've done, and this is probably the most important of them all, is they've controlled now the floating center conductor of the airline. So the airline, as I pointed out, is one of the key items that we're going to measure, and this airline has a floating center conductor. That center conductor is captured between the male and the female connectors at the ends of the VNA cables. Now, by design, that capturing of the center conductor cannot be a compression fit. If we have the male and female connectors pushing or putting pressure on that center conductor in a compression fit, it will cause the center conductor to bow or deform in shape. And we cannot allow that to happen. So by design, that means we must have some small tolerance between the male and female connectors on the ends of the cables that allow that center line, that airline center conductor, to float slightly to the left and to the right. That has to be done, and because that center conductor can float, that has in the past created a large amount of the measurement uncertainty and the non-repeatability of the calibration or the primary experiment with that airline. So one of the main things that METIS has introduced in the past decade was this concept of adding a small spacer, which is created out of Kapton material. So a small disc that is put on one end of the airline, and then they push the airline center conductor against that disc, and that disc provides then a very repeatable positioning of that center conductor between the male and female ends of the coaxial cables. And that repeatable positioning then, after they complete the mating of the center of the airline to the cables, that repeatable positioning gives them a much lower uncertainty during the primary experiment, and a much more accurate characterization of the calibration kit. This is one of the key things that has been created at Metis over the past decade. These three things are, from my point of view, an overall summary of what's been done to improve things. And the proof statement, I like this graph more than anything else I've seen. This graph is showing the results of an S21 measurement of a coaxial airline after calibration. And this is from 2013, published by Metis. So this data is, this has been out there for a while. It's been reviewed a lot. But what we see are two lines on this graph. The red line shows the state-of-the-art calibration using the 85052B calibration kit with a sliding load, so performing the most accurate calibration they could, and then measuring the S21 of the airline. You see this variation of approximately 0.01 dB in the S21 trace. So 0.01 dB, a very small number, something you might almost want to say, well, that's just not even that important. But in contrast to that, after they've applied these three things that I just mentioned, so they propagate their own uncertainty using VNA tools, they've improved the connector half pair modeling and de-embedding, and they positioned in a precise way the center conductor of that airline. After doing these three things, the result is the black trace, which is a much smoother line. Virtually at least an order of magnitude, if not 2 orders of magnitude, less variation on that line. It looks like a perfectly smooth line compared to the prior state-of-the-art results that we're seeing. There are other things that Metis has done to make a proof statement, and of course you could take a look at their papers in there. They published the results in a variety of ways, but this is one graph that I think really just captures what has happened and kind of drives that home. Now, what does this mean in practice? As I mentioned, I am an engineer. I want to take advantage of all these things that are being done around the world, research at the National Metrology Institutes. It sounds very official and very formal. They're making a ton of progress, but how do I take advantage of this in the lab when I'm using my network analyzer and my calibration kit and I'm not doing any research whatsoever? Well, this is how. Rohde & Schwarz has now changed our traceability tool chain to go directly to Metis. So we now send our primary calibration kits from our metrology lab at Rohde & Schwarz to Metis to be characterized. Metis characterizes them using the results of their primary experiment. So we're only one step removed from their primary experiment, giving us the best possible measurement uncertainty on our primary cal kits at Rohde & Schwarz. Then we use those primary cal kits to calibrate our network analyzers in the metrology lab, and that's when we characterize your calibration kits. So your calibration kits are now 2 steps removed from the primary experiment at Metis, and they arrive to you with characterization data and measurement uncertainty that's been propagated from the primary experiment. And how do we do this propagation? Well, the VNA Tools software was a key component of this, so we now install the VNA Tools software on our network analyzers so that you can take advantage of this characterized calibration kit when you calibrate your network analyzer. So what happens is you load the data from the thumb drive of the calibration kit into your network analyzer, and you perform a calibration, and all of the information during that calibration is transferred to VNA Tools. The measurement uncertainties are propagated forward just like they're done in the Metis lab, just like they're done in the Rohde & Schwarz metrology lab. They're done on your instrument, and they're propagated forward so that at the end of calibration, you see S parameters with uncertainty bands around the results that are calculated in real time. The calibration for you looks the same as any other calibration. So you still simply connect the standards like open, short, and match on port 1, open, short, match on port 2, and unknown through if you're doing the 8-error term model for a 2-port calibration. You just connect these standards like you would for any other calibration, but you just invoke a Metis calibration. You tell it that you want to propagate the uncertainties, and then that propagation happens in real time behind the scenes. You as the end user, you don't see any of the activity between the VNA and the Metis VNA Tools software. It just happens behind the scenes automatically, and you just see the measurement results in the end. So now, the question I get at this point quite often is, well, that's great, I see these really tiny measurement uncertainties on my S parameter traces, but how do I know if these are correct? And there's only one answer for that. The only way to really know that your measurements are correct is to run a verification test immediately after calibration. So a verification kit is very similar to a calibration kit, but different in that it has completely different standards. For instance, it might have or will have different impedance reflections, so offset shorts and things like this. It might have a BD line with a 25 ohm center conductor, and attenuators are also very common in a verification kit. So the concept is you get a verification kit that is also traceable back to the National Metrology Institute, so METIS in this case, also traceable back to the primary experiment, and it comes with its measurement uncertainty as well. And you launch the verification tool on the VNA. The verification tool looks like this, but is very similar to calibration. You simply get a list of standards, and you're asked to connect them one at a time. The standards will be swept from the verification kit, and the measured results by the network analyzer using the calibration you just performed, those measurement results will be compared to the expected results that are on the thumb drive that comes with the verification kit. Those calculations and that comparison, they are done by VNA tools again. So they're being done by what we call an independent third party, calculating all the uncertainties and comparing your measured result to what we expect and telling us, yes, you passed the verification test, or no, you failed the verification test. If you can pass the verification test, which is not trivial, you have to take great care. You have to really make good connections, best practices, minimize cable movement. But if you pass the verification test, which measures a variety of standards at a variety of frequencies, covering a wide range of the Smith chart in terms of reflections and a wide range of transmission attenuations, if you can pass the test, then you can be very confident that not only are you making correct measurements, but also the measurement uncertainty bands are correct as well, because the test is checking whether or not the expected results are falling within the measurement uncertainty of the measured results. So that's how you know if it's accurate. So if you do these two things, calibrate using the METIS cal, and then run a verification, and you pass the verification, at that point you can feel quite confident that what you see on the screen is accurate and the uncertainty bands are really the measurement uncertainty that you have for that particular measurement. That is how you would do it. And this is, by the way, this is how we, as just ordinary engineers in the lab, this is how we take advantage of all the research that's being done in the National Metrology Institutes around the world today, where measurement uncertainties from the very best primary experiment can be propagated down to the measurements you're making on your bench with your network analyzer in real time. So that's quite impressive from my point of view. That's a quick overview of what can be done. And the last thing I leave you with is the statement, the simple statement: it's time for you to start acting like a metrologist. Thanks a lot for your attention and watching, and we'll see you in the next video.